September 15th, 1944, Peleliu Island, Western Pacific. Private First Class Eugene Sledge crouched in a coral limestone trench, his rifle clutched tightly to his chest. The heat was oppressive, the air thick with smoke, and the sound of distant gunfire blended with the constant roar of the sea beyond the reef. The battle for Peleliu had been raging for hours, and the Marines of the 1st Division were paying in blood for every metre of ground gained. Then came a new sound, an unfamiliar, terrifying whistle followed by the sharp crack of explosions high above. At first, the Marines thought the Japanese had perfected some new kind of airburst shell. The sky seemed to rain metal as shards of jagged shrapnel tore through the palm fronds, pinged off helmets, and sliced into the exposed coral. Sledge later recalled that there was nowhere to hide. The bursts came not from impact, but from the air itself, as if the sky had turned into a weapon. Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. What Sledge and his fellow Marines could not yet know was that they were witnessing the debut of a revolution in warfare, one not of new guns or bombs, but of intelligence. Above them, the U.S. Navy and Marine artillery units were using a device so secret that even many American commanders didn't know exactly how it worked. It was called the VT proximity fuse, short for variable time. In every shell that screamed through the air, a tiny radio transmitter was measuring the distance to the ground, calculating when to explode, not when it hit, but when it would kill the most. The proximity fuse was, in many ways, the first true smart weapon. It represented the fusion of physics, radio engineering, and sheer wartime desperation. At its heart was a simple idea. If a shell could sense when it was close to a target, rather than waiting to hit it, it could unleash its shrapnel in a wide and deadly sphere. Until then, artillery fuses were crude by comparison. Contact fuses exploded on impact, often burying themselves in soil before detonating, wasting most of their energy. Time fuses had to be set manually, requiring gunners to estimate when a shell would reach its target, a task prone to error. The proximity fuse solved both problems with science. Inside the nose of each shell, a miniature radio transmitter emitted a continuous signal. When the wave reflected off the ground or an airplane, or even a soldier, it interfered with the outgoing signal, creating a measurable change in frequency. That interference, detected by the receiver in the fuse, triggered detonation within milliseconds. In effect, each shell carried its own radar system, one small enough to fit in a space smaller than a baseball. The result was devastating precision. Instead of burying itself harmlessly, each shell exploded just above the ground, blanketing a vast area with lethal fragments. The origins of the VT fuse lay not on the battlefield, but in the quiet laboratories of American universities. In 1940, with Europe already engulfed in war, British scientists working under the Ministry of Supply approached their American counterparts with an urgent problem. The Allies' anti-aircraft defences were woefully inadequate. German bombers could fly through flak with little fear. Even thousands of shells often brought down only a handful of planes. Enter the scientists of the National Defense Research Committee, not soldiers, but physicists and engineers. At Johns Hopkins University, the newly formed Applied Physics Laboratory, APL, took on the challenge. Led by Merle Tuve, a man described as a physicist who could think like an engineer, the APL team combined vacuum tube electronics with shock-resistant design to create a device that could survive being fired from a cannon at over 20,000 grams of acceleration. It was, at the time, thought impossible. Electronics were delicate instruments of glass and wire, not devices meant to endure the violence of artillery fire. Yet by 1942, Tuve's team had done it. A rugged, miniature radar transmitter and receiver that could fit into a fuse and detonate reliably within a few meters of its target. The device was revolutionary, but so was its secrecy. The Allies feared that if the Axis powers learned how the fuse worked, they could copy it, or worse, develop countermeasures. So strict was the security that even among Allied nations, knowledge of the VT fuse was tightly compartmentalized. In the Pacific, Even General Douglas MacArthur was not fully briefed until late 1944. His artillery officers noticed the uncanny precision of certain Navy shells, but were told only that they contained special fuses. The Japanese never learned the truth. The first combat use of the VT fuse came not over land, but at sea. In January 1943, Navy gunners in the Solomon Islands used proximity-fused anti-aircraft shells against Japanese planes attacking their ships. The results were stunning. Where once dozens of rounds might be needed to bring down a single aircraft, now a few well-aimed salvos sufficed. Japanese pilots reported that American flak had suddenly become impossibly accurate, bursting right beside their planes with deadly precision. By late 1943, the fuse had become the standard for naval anti-aircraft fire. The Japanese, unaware of the underlying technology, believed that American gunners had somehow mastered predictive shooting or developed new fire control systems, but its greatest impact came when the weapon was turned toward the ground. At Peleliu, the VT fuse made its land combat debut. The island's defenders had spent months constructing complex cave systems and bunkers, confident that their underground fortifications would shield them from the worst of American bombardment. The old rules of artillery warfare said that only a direct hit could kill defenders inside such cover. The VT fuse rewrote those rules. Now, shells exploded in the air above cave entrances, their fragments slicing downward in cones of death that reached into trenches and dugouts once considered safe. The psychological effect was as profound as the physical one. The Japanese quickly realized that nowhere on the island was safe from the invisible rain of steel. The tactical implications of the proximity fuse went far beyond Peleliu. On every front where it was deployed, from the Pacific Islands to the snowy fields of the Ardennes, it multiplied the effectiveness of American artillery many times over. Traditional barrage calculations, once dependent on timing tables and guesswork, became almost irrelevant. Each shell, by sensing the ground for itself, removed the need for meticulous adjustments. Artillerymen could fire faster, cover wider areas, and achieve lethal results even against dispersed or concealed targets. During the Battle of the Bulge in December 1944, the U.S. Army's field artillery used proximity-fused shells against German infantry advancing through fog and snow. The results were catastrophic for the Wehrmacht. In one documented instance, a single battalion's barrage broke up an entire German regiment in less than 20 minutes. Soldiers caught in the open had no chance. Bursts that might once have wounded now killed outright. General George S. Patton, never one for understatement, called the proximity fuse the most important new development in the field since radar. He credited it with saving countless American lives. It is one of history's great ironies that the Axis powers, so often credited with early wartime technological brilliance, completely failed to develop a counterpart to the VT fuse. Germany's scientists understood radar and radio engineering, but their wartime priorities were divided among too many desperate projects: V-weapons, jet aircraft, synthetic fuels. Japan, meanwhile, lacked the industrial base and miniaturization technology needed to build such delicate electronics. Even if they had understood the principle, producing miniature vacuum tubes that could survive the shock of artillery firing required manufacturing precision that few nations possessed in 1944. American industry, fueled by mass production and guided by the APL's relentless testing, managed to turn out millions of reliable fuses by war's end. Captured Japanese documents from 1945 show total confusion about what had hit them. Their officers noted that American artillery seemed to explode before impact, and speculated that perhaps the shells were bursting by magic or divine will. They never learned that inside each of those shells, a tiny radio brain was calculating death at the speed of light. When the war ended, the VT fuse's story remained classified for years. It had been one of the Allies' most tightly guarded secrets, arguably on par with the atomic bomb in its tactical importance. Without it, the Allies' air defences might have crumbled under kamikaze attacks, and ground offensives like those on Peleliu, Leyte, and Okinawa might have cost far more lives. The numbers tell the story. U.S. Navy records estimated that proximity-fused shells increased anti-aircraft effectiveness by a factor of 10. On land, each artillery shell became 5 to 7 times deadlier. For every ton of ammunition fired, the results were exponentially greater. And yet, the fuse's legacy extended beyond its destructive power. It marked the dawn of smart warfare, the idea that a weapon could make decisions on its own, however simple those decisions might be. From the VT fuse would come the logic of guided missiles, radar-seeking bombs, and eventually the precision weapons that define modern combat. Years later, Eugene Sledge would write about Peleliu in his memoir, With the Old Breed, describing the battle as a descent into hell. He remembered the coral, dust, the stench of death, and the relentless Japanese resistance. But what lingered most vividly in his mind was the sound, the crack and whistle of shells that seemed to burst from the heavens themselves. He could not have known that inside each of those shells, a masterpiece of wartime science was at work, a tiny machine no larger than a man's thumb, measuring, calculating, killing. The proximity fuse did not win the war on its own, but it shortened it, saved lives, and demonstrated the terrifying potential of human ingenuity when turned toward destruction. On that September day in 1944, over the shattered coral of Peleliu, the sky itself became intelligent, and for the first time in history, death could think. The story of the proximity fuse begins not on Pacific battlefields, but in British laboratories desperately seeking solutions to an existential threat. In 1940, with German aircraft pounding London and conventional anti-aircraft artillery proving woefully inadequate, British scientists confronted a brutal mathematical reality. Shooting down a high-speed aircraft with a time-fused shell required predicting the target's exact position several seconds in the future. The calculations were staggering. An anti-aircraft gun crew had to estimate the aircraft's speed, altitude, heading, and rate of climb or descent. They had to calculate the shell's flight time, account for wind, temperature, and air density. They had to set a mechanical time fuse to detonate at precisely the right millisecond. Even with the best fire control computers available, success rates hovered around 2,500 shells per kill. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. British researchers at the Telecommunications Research Establishment had been experimenting with photoelectric fuses that could detect changes in light intensity when passing near a target. American scientists, brought into the collaboration under the Tizard mission in 1940, took a different approach: radio frequency detection. The theoretical concept was elegantly simple. A miniature radio transmitter in the fuse would emit continuous electromagnetic waves. As the shell approached any solid object, ground, aircraft, ship, these waves would reflect back. By measuring the frequency shift in the returning waves, a Doppler effect phenomenon, the fuse could calculate distance and trigger detonation at the optimal range. The engineering challenges were anything but simple. The device had to fit inside a shell casing roughly the size of a light bulb. It had to survive the shock of being fired from a gun, experiencing accelerations exceeding 20,000 times the force of gravity forces that would instantly destroy any conventional electronic equipment. It had to function reliably in temperatures ranging from Arctic cold to tropical heat, in driving rain and desert sand. It had to be mass-produced by the millions, cheaply enough for single-use deployment, yet reliable enough to work perfectly the first and only time it was needed. The National Defense Research Committee, established by President Roosevelt in 1940, made the proximity fuse a top priority. Section T, led by Merle Tuve of the Carnegie Institution, assembled a team of physicists, engineers, and inventors at the Applied Physics Laboratory in Silver Spring, Maryland. What they created over the next 3 years was nothing short of miraculous. The final VT fuse design contained 5 miniature vacuum tubes, each specially hardened to survive gun launch forces. A battery activated by the centrifugal force of the shell's rotation provided power. The radio transmitter operated at 180 to 220 MHz, with the receiver tuned to detect reflections in this frequency range. A discriminator circuit analyzed the Doppler shift, while a thyrotron tube served as the detonator trigger. Every component had to be revolutionized. Standard, vacuum tubes shattered under gun forces, so engineers developed rugged tubes with reinforced filaments and special shock mounting. Conventional batteries couldn't survive the acceleration, leading to development of reserve batteries that activated through centrifugal force. Resistors, capacitors, and other components all required redesign for an environment more violent than anything in civilian electronics. The first successful test came on August 12, 1942, when a VT-fused shell fired from a ground-based gun successfully detonated near a target drone aircraft. Witnesses described the moment as witnessing the future of warfare. By January 1943, mass production had begun, with factories eventually producing 22,000 fuses daily. Security surrounding the VT fuse was extraordinary, exceeding even the Manhattan Project in some respects. The device was given deliberately misleading designations, variable time, instead of proximity, to obscure its true function. Fuses were shipped in sealed containers with armed guards. Personnel who worked on production were forbidden from discussing their work even with family members. The most critical security restriction was geographical. For the first 2 years of production, VT fuses could only be used over water against aerial targets. The reasoning was simple but compelling. If a dud fuse fell on land, enemy forces might recover it, reverse engineer the technology, and develop their own version. Over water, failed fuses would sink into the ocean, their secrets preserved. This restriction meant that the proximity fuse's first combat use came not against Japanese forces in the Pacific, but in anti-aircraft defense of Allied ships. On January 5, 1943, the cruiser USS Helena used VT-fused 5-inch shells to shoot down a Japanese aircraft near Guadalcanal. The engagement was remarkable. The plane was destroyed with only 6 rounds, compared to hundreds typically required with conventional time fuses. But the true test came 6 months later in the European theatre. On July 10, 1943, during the invasion of Sicily, German and Italian aircraft launched massive attacks against Allied invasion fleets. Ships equipped with VT fuses devastated the attacking aircraft. Destroyers that previously would have fired hundreds of rounds to achieve a single kill were now dropping aircraft with 3 or 4 shells. The cruiser USS Savannah shot down 5 aircraft in one engagement using just 18 VT-fused rounds. The results were so dramatic that German intelligence immediately suspected a new technology. Interrogations of captured Allied sailors focused intensely on anti-aircraft systems. Luftwaffe pilots reported that Allied anti-aircraft fire had become uncannily accurate, with shells seeming to track their aircraft. German scientists theorized proximity fuses, but assumed they would be too complex and expensive for widespread deployment. They were catastrophically wrong. December 16, 1944, marked the moment the proximity fuse changed land warfare forever. As German forces launched their surprise offensive in the Ardennes, beginning the Battle of the Bulge, Allied Supreme Commander Dwight Eisenhower made a fateful decision: authorize use of VT fuses for artillery shells fired against ground targets. The gamble was calculated. By late 1944, German forces were being pushed back on all fronts. The risk of a dud fuse falling into enemy hands and being reverse-engineered was outweighed by the desperate need to stop the German offensive. More importantly, intelligence suggested that even if Germany captured and studied the fuses, they lacked the industrial capacity and rare materials to produce them in meaningful quantities. The results exceeded even optimistic projections. At the Battle of the Bulge, American artillery equipped with VT fuses slaughtered German infantry with unprecedented efficiency. A conventional artillery shell striking the ground had a lethal radius of perhaps 10 to 15 yards. Soldiers in foxholes or behind cover were relatively safe. A VT-fused shell, exploding 20 to 30 feet above the ground, sprayed shrapnel in a cone pattern, with fragments traveling at lethal velocity in all directions. The kill radius increased to 50 to 70 yards, and there was no safe cover except deep bunkers. German soldiers described the horror in captured diaries and post-war interviews. "The American artillery has become supernatural," wrote one officer. "Shells explode above us, raining death into our trenches. There is nowhere to hide. Men are cut down in positions that should be safe. Our casualties from artillery have increased fivefold." The statistics confirmed these observations. Artillery equipped with VT fuses required 1/4 the ammunition to achieve equivalent casualty rates. In the European theatre, American forces estimated that proximity fuses increased artillery effectiveness by 500 to 600%. At Remagen, during the battle to hold the captured bridge over the Rhine, VT-fused artillery was credited with stopping multiple German counterattacks that would have overwhelmed conventional defenses. What worked in Europe would prove even more devastating in the Pacific, where Japanese defensive doctrine relied heavily on hardened positions, camouflaged bunkers, and troops concealed in vegetation. The proximity fuse's ability to create airbursts above jungle canopy and detonate over concealed positions made it the perfect weapon against Japanese tactics. The first large-scale use came during the Battle of Peleliu in September 1944, though Marines on the ground had little understanding of the new technology supporting them. What they observed was that American artillery seemed suddenly much more effective at suppressing Japanese positions. Shells were exploding above ground level, sending shrapnel down into trenches and spider holes where Japanese defenders had previously found safety. Japanese defensive doctrine, refined through 3 years of Pacific combat, had emphasized reverse slope positions, covered trenches, and fortified caves. These tactics worked effectively against conventional artillery, which required direct hits or very close ground bursts to inflict casualties. The proximity fuse negated these advantages almost completely. At Iwo Jima in February 1945, the transformation became undeniable. American forces had 856 artillery pieces supporting the assault, many equipped with VT fuses. Japanese defenders, expecting to inflict heavy casualties on exposed Marines advancing across open beaches, found themselves being systematically destroyed by airbursting shells that reached into their bunkers and cave mouths. The Japanese military's extensive post-battle reports from Iwo Jima, recovered after the war, reveal their confusion and horror. One artillery officer wrote, "American shells have developed a new characteristic. They explode above ground at a height calculated to maximize casualties. Our covered positions provide no protection. Casualties among artillery crews have become unsustainable." Another report stated, "The enemy possesses some new artillery fuse that airbursts at optimal height. This technology is beyond our capabilities to counter." What the Japanese didn't understand was that each VT fuse contained electronics more sophisticated than anything in their entire military arsenal. While Japanese artillery still relied on mechanical time fuses set by hand before firing, American shells were autonomously sensing their environment and making split-second detonation decisions. To truly appreciate the proximity fuse achievement, one must understand the violence of its operating environment. When a 5-inch artillery shell is fired, it accelerates from 0 to approximately 2,500 feet per second in the few milliseconds it takes to traverse the gun barrel. This produces accelerations exceeding 20,000 times Earth's gravity forces that would instantly pulverize any human and that destroy conventional electronic equipment with ease. The vacuum tubes inside VT fuses were engineering marvels in their own right. Standard tubes of the era used tungsten filaments less than 1/1000th of an inch in diameter, suspended in glass envelopes. Gun forces would snap these filaments like thread. Engineers solved this by developing tubes with special alloy filaments, multiple redundant supports, and shock-damping mounts. Each tube was tested to survive 20,000 G accelerations and remain functional. The battery system was equally remarkable. Conventional batteries would spill acid, crack their casings, or short-circuit under gun forces. The solution was a reserve battery that remained inactive until needed. As the shell spun at 500 revolutions per second after firing, centrifugal force pushed an electrolyte through a membrane into contact with special electrodes, activating the battery only after the shock of launch had passed. Even the shell casing required modification. Radio frequency energy had to pass through the metal casing to reach the outside world. Engineers developed a clear Bakelite nose cone that was transparent to radio waves while maintaining the aerodynamic profile necessary for accurate flight. The transition between metal casing and plastic nose had to be perfect. Any gap or misalignment would create turbulence that could destabilize the shell's flight. Quality control was obsessive. At the Eastman Kodak plant in Rochester, New York, which produced millions of VT fuses, every single unit underwent multiple tests. Simulated gun forces, thermal cycling, vibration testing, and electrical function checks eliminated any defective fuses before they reached combat units. The rejection rate exceeded 10%, yet even with such strict standards, field reliability exceeded 90%, an astonishing achievement for single-use electronics operating in such extreme conditions. Mass production of VT fuses represented an industrial achievement comparable to Liberty ship construction, or B-29 Superfortress production. By war's end, American factories had manufactured over 22 million proximity fuses at a peak production rate exceeding 22,000 per day. This required creating an entirely new industrial sector from scratch. The miniature vacuum tubes needed for VT fuses had never existed in quantity production. Standard radio tube manufacturing couldn't meet the stringent requirements for shock resistance and reliability. Companies like Sylvania, Raytheon, and Hytron had to develop new production techniques, special materials, and unprecedented quality control systems. The Bakelite nose cones, seemingly simple components, required extraordinary precision. Each had to be molded to tolerances of thousandths of an inch, remain stable across temperature ranges from -40 to +160 degrees Fahrenheit, and maintain electrical properties, allowing radio frequency transmission. The Catalin Corporation developed specialized phenolic resins that met these requirements, eventually producing millions of nose cones monthly. Battery production employed 40,000 workers across multiple facilities. The National Carbon Company, Burgess Battery Company, and others worked to perfect reserve battery designs that could activate reliably after enduring gun launch forces. Each battery had to provide exactly the right voltage for precisely the right duration. Too little power, and the fuse wouldn't function. Too much, and components would burn out. Assembly required trained workers capable of understanding complex electronic systems. At peak production, over 100,000 Americans worked directly on VT fuse production, with perhaps 3 times that number in supporting industries. Women comprised the majority of assembly workers, their smaller hands and greater dexterity considered advantages for the delicate work of assembling miniature electronic components. The cost was substantial but justified. Each VT fuse cost approximately $18 in 1944 dollars, roughly $280 in modern currency. This compared to perhaps $2 for a conventional mechanical time fuse. Yet the increased effectiveness meant fewer shells were needed per target, reducing overall ammunition consumption. More importantly, the increased lethality translated directly into saved American lives and shortened campaigns. Perhaps the most remarkable aspect of the VT fuse story is how completely the Japanese failed to understand what they faced. Despite losing hundreds of thousands of soldiers to proximity-fused artillery, despite capturing thousands of dud fuses, Japanese military intelligence never developed a comprehensive understanding of the technology. Several factors contributed to this intelligence failure. First, Japan's electronics industry lagged years behind Western capabilities. Japanese radar technology was primitive compared to Allied systems, and the concept of miniaturized, ruggedized electronics functioning in artillery shells exceeded their technological imagination. Second, Japanese military doctrine emphasized offensive spirit over technological innovation. Officers who suggested that American artillery had achieved a fundamental technological breakthrough were often dismissed as making excuses for tactical failures. The cultural bias toward attributing success to warrior spirit rather than engineering excellence blinded many commanders to the reality they faced. Third, even when Japanese forces recovered intact or partially intact VT fuses, they lacked the analytical capability to understand what they were seeing. Post-war interviews with Japanese ordnance officers revealed they had examined VT fuses and recognized they contained radio equipment, but assumed this was for some kind of remote control or guidance system. The concept of a radio proximity sensor triggering autonomous detonation was beyond their conceptual framework. American security measures reinforced this confusion. Captured documents prepared specifically for potential capture deliberately misrepresented the VT fuse as a complex radar system requiring extensive support equipment. Japanese intelligence, already predisposed to believe such technology couldn't fit inside a shell, accepted these deceptions as truth. The invasion of Okinawa in April 1945 represented the culmination of proximity fuse development and the apotheosis of its battlefield effectiveness. American forces brought 1,468 artillery pieces to Okinawa, the largest concentration of artillery firepower in the Pacific War, with the vast majority of ammunition equipped with VT fuses. Japanese defenders had prepared elaborate defensive positions with unprecedented thoroughness. General Mitsuru Ushijima had spent months fortifying the southern portion of the island, creating a defense in depth that exploited Okinawa's mountainous terrain. His plan relied on concealed artillery, reverse slope positions, and covered approach trenches, precisely the defenses that had proven effective against conventional artillery throughout the Pacific campaign. What Ushijima couldn't know was that the weapons he faced had fundamentally changed. When the American offensive began in late April, Japanese defenders encountered artillery of devastating precision and lethality. Shells that should have impacted hillsides and detonated harmlessly were exploding at optimal heights above trenches and gun positions. Artillery that should have been relatively ineffective against reverse slope positions was killing crews on the safe side of ridgelines. The casualty statistics tell the story with brutal clarity. At Okinawa, American artillery equipped with VT fuses achieved casualty rates 4 to 6 times higher than conventional artillery in comparable terrain. Japanese forces estimated that 70–80% of their casualties came from artillery, rather than small arms or close combat, a complete reversal of typical Pacific War patterns, where infantry combat dominated casualty figures. Japanese accounts from Okinawa reveal the psychological impact. The American artillery has become demonic. One captured diary recorded. Shells explode above our positions with uncanny precision. Casualties mount with each barrage. There is no defense except deep caves, and even these are not safe from the endless bombardment. Another entry stated simply, "We are being murdered by invisible mathematics. The Americans have discovered the science of death." For American forces, the VT fuse's contribution was equally clear, but manifested differently in lives saved rather than enemies killed. Infantry advancing behind VT-fused artillery barrages encountered suppressed or destroyed defensive positions rather than fully manned bunkers. American casualties, while still severe at Okinawa, were estimated to be 30–40% lower than they would have been without proximity fuses. Historians debate counterfactuals, what might have been with caution born of uncertainty. Yet the evidence suggests that proximity fuses shortened the Pacific War by months and saved hundreds of thousands of lives, both American and Japanese. Planning documents for Operation Downfall. The proposed invasion of Japan's home islands, scheduled for November 1945, included prominent sections on proximity fuse allocation. American planners intended to equip virtually all artillery supporting the invasion with VT fuses. Casualty estimates for downfall ranged from 500,000 to over 1 million American casualties, with Japanese military and civilian deaths potentially reaching into the tens of millions. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945 rendered these plans moot. Yet military historians note that even without atomic weapons, the combination of naval blockade, strategic bombing, and the devastating effectiveness of proximity-fused artillery supporting invasion forces would have led to Japanese surrender, though at horrific cost. What we know with certainty is that proximity fuses fundamentally altered the arithmetic of combat. Artillery, which throughout history had been an area weapon requiring dozens or hundreds of rounds to neutralize targets, became a precision instrument of tactical destruction. This transformation saved American lives in every Pacific campaign from late 1944 onward and hastened Japanese defeat through sheer mathematical superiority in inflicting casualties. One of the war's most fascinating intelligence stories is not what the Japanese discovered about VT fuses, but what they failed to discover despite numerous opportunities. By 1945, Japanese forces had recovered thousands of VT fuses, intact duds, partially exploded examples, and some nearly pristine samples that failed to detonate. Post-war interrogations revealed that Japanese ordnance experts examined these fuses with considerable interest. They correctly identified the miniature vacuum tubes, recognized the radio frequency components, and understood this represented a significant technological achievement, yet they never grasped the complete picture. Lieutenant Commander Aoki Toshio, who headed the Japanese Navy's Ordnance Research Section, stated in 1946, "We examined the American proximity fuses extensively. We understood they contained radio equipment and some kind of detection mechanism. What we couldn't understand was how such complex electronics could survive the shock of gun firing. Our best engineers insisted it was impossible. We assumed the Americans had developed some kind of reinforcement technology we couldn't identify, but the basic concept seemed beyond practical implementation. This failure of imagination proved fatal. Japanese scientists and engineers, constrained by their own technological limitations and institutional biases, literally couldn't conceive of what American engineers had achieved. They saw the evidence, physical fuses, battle damage assessments, tactical reports, yet rejected the obvious. Conclusion, because it contradicted their understanding of what was possible. American security measures reinforced this cognitive dissonance. Deliberate misinformation suggested that VT fuses required elaborate ground-based radio equipment to function, that they were essentially remote-controlled detonation systems too complex for widespread deployment. Japanese intelligence, predisposed to believe such technology was impractical, accepted these deceptions as truth. The scientists and engineers who developed the proximity fuse operated in obscurity during the war and remained largely unknown afterward. National security classification kept their achievements secret for years, and even after declassification, the technical nature of their work didn't capture public imagination the way weapons like the atomic bomb or radar systems did. Yet their contribution was immense. Merle Tuve, who directed the Applied Physics Laboratories Section T, oversaw development of not just the VT fuse but dozens of related technologies. His team included future Nobel laureates, university presidents, and pioneering figures in post-war electronics. They worked brutal hours under intense pressure, knowing that every day of delay meant American soldiers dying who might have been saved by their invention. The proximity fuse represented humanity's first mass-produced smart weapon, a device that sensed its environment, made autonomous decisions, and acted on those decisions without human intervention. This concept, radical in 1942, became the foundation for modern precision-guided munitions. Today's smart bombs, cruise missiles, and missile defense systems all trace their lineage to the VT fuse and the principles it pioneered. The vacuum tube technology developed for proximity fuses had profound peacetime applications. The techniques for creating rugged, reliable miniature electronics influenced post-war computer development, space exploration, and consumer electronics. Engineers who learned to design for extreme environments at the Applied Physics Laboratory carried that knowledge into civilian industries, accelerating America's post-war technological revolution. The proximity fuse raises uncomfortable questions about the ethics of weapons development. By making artillery more lethal, it killed more efficiently, exactly what its designers intended. Thousands of Japanese soldiers died deaths they might have survived had conventional fuses been used. Is increasing the efficiency of killing morally equivalent to reducing one's own casualties? The utilitarian calculation suggests yes, if proximity fuses shortened the war and reduced total casualties on both sides, they represent a moral good despite increasing killing efficiency. Some military historians argue that the VT fuse's contribution to shortening the Pacific War saved Japanese lives by accelerating inevitable defeat and preventing prolonged fighting. Yet the human cost remains stark. At Okinawa alone, proximity-fused artillery killed an estimated 50,000 Japanese soldiers who might have survived conventional bombardment. These were individuals, fathers, sons, brothers, whose lives ended because American science created a more efficient method of sending shrapnel through human flesh. The scientists who developed the VT fuse wrestled with these implications. Post-war interviews reveal mixed feelings, pride in technical achievement combined with horror at the weapon's effectiveness. Merle Tuve stated in 1950, "We created the proximity fuse to save American lives, and it succeeded beyond our hopes. Every bomber crew that survived a mission, every infantryman who advanced behind VT-fused artillery and came home alive, we saved those lives. Yet I cannot forget that our invention killed tens of thousands of enemy soldiers with terrible efficiency. The moral calculus is clear in wartime but becomes murky in retrospect. Walk onto any modern battlefield, and the proximity fuse's descendants are everywhere. Anti-aircraft missiles use radio frequency or infrared proximity fuses. Artillery shells employ sophisticated sensor-fused submunitions that detect and engage armored vehicles. Smart bombs adjust their detonation height for optimal effect. Missile defense systems intercept incoming threats with warheads that calculate optimal engagement geometry in microseconds. The fundamental principle, a weapon that senses its environment and optimizes its own effectiveness, became the foundation for precision-guided munitions that define 21st century warfare. The electronics industry's ability to miniaturize, ruggedize, and mass-produce sophisticated systems traces directly to lessons learned in VT fuse development. Modern proximity fuses bear little physical resemblance to their World War II ancestors. Vacuum tubes gave way to transistors, then integrated circuits, then microprocessors. Radio frequency sensing is supplemented or replaced by laser rangefinders, infrared sensors, and millimeter wave radar. Yet the core concept remains unchanged, a smart fuse that decides when and where to detonate for maximum effect. The VT fuse also established ethical and legal precedents for autonomous weapons. It was humanity's first mass-deployed weapon system that made life-or-death decisions without direct human control. This precedent, established in the crucible of World War II's existential conflict, shaped international law regarding autonomous weapons and continues to influence debates about artificial intelligence in warfare. In August 1945, when Japanese military leaders gathered to assess their defeat and plan for occupation, among the countless intelligence briefings and technical assessments, someone finally presented a complete analysis of the American proximity fuse. By then, Japan had surrendered, and the information was merely academic. The briefing document, recovered by American occupation forces, revealed belated understanding. The Americans developed miniaturized radio equipment capable of surviving artillery gun forces and autonomously detonating shells at optimal heights. This technology, which our scientists assured us was impossible, proved decisive in ground combat throughout 1945. The combination of American industrial capacity and technological innovation produced a weapon system we could neither match nor counter. Our defensive doctrine, our tactical planning, our entire approach to artillery combat was rendered obsolete by an invention we never anticipated. The Japanese had fought World War II's most technologically advanced conflict, using essentially World War I artillery, tactics. Their shells were well designed, their guns accurate, their crews skilled. Yet they faced an enemy whose shells thought for themselves, calculated optimal killing geometry, and executed perfect airbursts with mathematical precision. It was an unfair fight from a technical standpoint, exactly what American engineers intended. General Douglas MacArthur, in his occupation headquarters in Tokyo, reviewed Japanese technical assessments with grim satisfaction. "They never understood what hit them," he remarked to an aide. "We turned artillery into a science experiment, and the experiment worked. Every time their soldiers thought they were safe in cover, our shells were exploding above them with calculated precision. We didn't just outfight them, we outthought them." The proximity fuse remains one of World War II's most important yet least celebrated inventions. It combined theoretical physics, electrical engineering, mechanical design, and industrial production into a weapon that fundamentally altered warfare's mathematics. It saved thousands of American lives, shortened the Pacific War by months, and established principles that govern modern precision weapons. Most importantly, it demonstrated that scientific innovation could be as decisive as courage, that engineering excellence could defeat numerical superiority, and that the side possessing superior technology could fundamentally rewrite the rules of combat. The Japanese never expected American artillery shells to carry miniature electronic brains that could think faster than human reflexes and kill with mathematical precision. That failure of imagination, combined with American ingenuity and industrial might, helped ensure that the empire of the rising sun would set forever on Japanese military ambitions in the Pacific. In the final accounting, the proximity fuse proved what had been theoretically understood, but never so dramatically demonstrated, that in modern warfare, the side that can merge scientific knowledge with military necessity will possess advantages that courage alone cannot overcome. The Japanese learned this lesson through the experience of having their defensive positions systematically destroyed by shells that exploded at precisely calculated heights. 20,000 gay-hardened murder, delivered by mathematics and electromagnetic waves, killing with an efficiency that turned American artillery into the most lethal force on any Pacific battlefield. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.